Hello, everyone. My name is Dr. Clement Chumesi. I'm a medical statistician for the Norfolk Department of Medicine at the University of Oxford. So this particular YouTube video you're watching is part of a master class that I did for the National Union of Ghanaian Students in China. But it is open for everyone to watch and learn at their own pace. So please, if you are watching any other part apart from part one, don't forget to watch the previous part. So if you are watching part two, please watch part one and part two before you watch part three. If you are watching part two, please don't forget to watch the first part or first session before you proceed. Okay, so thank you very much, and I hope you enjoy the video. And please don't forget to subscribe. Your subscription is much really appreciated, and it is one way of supporting us, and we really appreciate it. Thank you very much. Enjoy. Cheers.
We would ask him outside, depending on how he wants it to go. So, Dr. Chumesi, I would call on you, and the flow of the training is entirely up to you, how you want to go about it. So, just give us the feedback, and if there's anything we can do to support you, we are happy to do it because we know that you are giving us your invaluable time in supporting this. Thank you very much.
All right. Thank you. And please, can you hear me?
Yes, please.
Yes, we can hear you, but it's a bit faint. If you can push it up a little bit.
Can you hear me
Yes,
now?
a lot better, sir. Thank you very much.
Okay. I don't know whether I'm able to also record from my end. Let me see if it works. But you started a recording, isn't it?
Yes, please.
Okay, so maybe after the session, if you could let me have the recording,
All right.
that would be
All
great.
right, please.
Okay, so I will share my screen and briefly take us through. Um, okay. So can you see my desktop, please?
Yes, please.
Yes, please, sir, we can say it.
Okay, that's fine. All right. Thank you very much once again um, for this opportunity to always share with students and other researchers. I'm very humbled. Okay, so today, before we go on to today's class, I'll quickly touch a bit on some platforms and other information I think you should know. So first of all, there's a YouTube channel that I already have that is on advanced data analysis in R. So once you get this particular script, or you can just go online and just search with my name. So once you search Clement Chumesi on YouTube, you get access. So on the channel you find access to range of videos already on the channel. So from learning how to program R from scratch up to, I mean, the most important things you need to know in statistics, and most of the let me say tutorials that sometimes I do in Oxford, I even upload them on my YouTube channel. Yeah, so it means that it has range of and then all the previous meetings that I've done with NUCSA China and other student unions are all on the channel. So it means that once you go there, you'll be able to learn at your own pace. So at the end of the day, after today's class, I would also try and upload it there so that you can learn at your own pace. Yeah. So, and there's a platform called Piazza that I use to manage um, the, the programming codes and everything. So this is to say that once you are watching the YouTube channel, all the programming codes you see, including today's lesson, you'll be able to access it on that platform called it's a platform called Piazza. It allows us to be able to, so for instance, all the previous material. So for instance, Luxa China Masterclass 2022, everything that was used can be found there, for instance. Yeah. So it means that by the end of the today's session, I would also upload all the relevant materials we use for today on the Piazza. But in order to be able to access the Piazza platform, you will need to send, first of all, your email address to me to sign up. Yeah. So, and then if you want to send your email address to me, I think if I click on this, so my email is, so you could either use any of them. So that's my Oxford email address, and the next one is my Gmail. Yeah, so it means that once you just go to Google and you type my name, so for instance, if you just go to Google and you type my name, just a minute, you'll be able to find my Oxford account. So you just click on that, and then you'll be able to access any of my emails. Yeah, so just send me an email that you want to enroll on the Piazza platform. That will help you to be able to have full access to all the programming stuff you see on the YouTube channel, as well as what you're going to do for today's lesson. Yeah, so that's just a quick one. So what are going to be some of the learning objectives? I must confess that I was pressed with time, so it meant I only started developing the outline and everything for today's class just this morning when I woke up. Yeah, so it was because of other unfortunate circumstances. But apparently, by the end of today's lesson, we are first of all going to learn a bit about some of the advanced or modern statistical methods that you can use for your research. And then we will talk a bit, brief introduction to what statistical programming is all about. How is it different from programming in the context of, let's say, computer science, engineering, and other disciplines. And then we'll talk a bit about the IDEs. IDEs is something we call integrated development environment. It's basically a platform that we use to run programming languages or softwares. And so we'll talk a bit about them. And then we'll learn how to import different data structures into R. So it means by the end of this meeting, suppose, let's say, previously you did your analysis in SPSS. You previously did your analysis in SAS. You previously did your analysis in Stata, but now you want to be able to do it in R. What that means is that you can actually import the Stata data, the SPSS data, the SAS data directly into R and perform your analysis. Unfortunately, because I couldn't get enough time to go about the third phase. So the third phase was just to do a practice task based on a medical application. So it means that we're going to now learn, at least apply two or one of the advanced or modern statistical methods that you should be aware of. So we're just going to focus on survival analysis and look at the model which extends the classical survival analysis. So it means that there is something called multi-state. Let me change this. So this is multi-state Markov modeling. Okay, yeah. So we're going to learn something about an extension to the standard survival models, which I'm very sure that many people are not aware of. But time couldn't permit me to wrap up all the course. So I was in the process and I noticed my time was almost up. So briefly, we'll do our best. And then if anything, I'll add relevant links for students to, or for everyone to just proceed from there. Okay, so now without wasting time, we are just going to talk a bit about some of the advanced, let me copy this briefly. Yeah, so we are going to talk a bit about some of the advanced statistical methods out there. So this is just to say that by the end of this particular session, which I'm about to talk about, you should be able to have a fair idea about existing statistical methods and when and how to use it, right? So the first one is called generalized linear models. And unfortunately for you, I've covered most of these methods on the YouTube channel already, just that there are a couple of new ones that I've not touched on. So it means that once you get access to the YouTube channel, you'll be able to learn most of, including power analysis, how to determine the minimum sample size needed to achieve some amount of power for your study and all sort of things. So there are so many materials there. So don't forget to make use of the YouTube channel as well. And please do help with the subscription. Thank you. All right, so the first one is generalized linear models. So now, basically, what are generalized linear models? So if you've heard of regression, regression is situations where we have some predictor, it's some set of predictors, and we want to see how, okay, someone is asking a question. If I visit YouTube. Oh, okay. So someone is asking where to start from if you visit my YouTube channel, since the person is like new. So basically, it depends on what you want. So if you want to learn how to program R or work in R from scratch, then you start with the first video here. So that's why I called it first lesson. And then we have second lesson, third lesson in that fashion. Okay, so it means that is if you want to start from R programming from scratch. And if you want to rather know, because remember that the knowledge of programming is not just about ability to just develop codes. No, you have to understand the statistics itself. So it means the statistics and the statistical programming must complement each other. This is to say that anything you do in a statistical software, whether it's a programming software, whether you are doing it in SPSS, whether you're doing it in Stata, any wrong thing you do, or you are doing it in GraphPad, Python, or whichever, any wrong thing you do, you get an output. So it means that once the mere fact that you got an output from any statistical analysis does not make it right. So this is to say, knowing the right tool for the right job is very important. So so it means that if you start watching any of these videos here, so let's say, okay, so there's a video on introductory statistics session 1. These are all just more of I would say theoretical, but very like simplified so everyone can understand. So this is if you want to now know when to use and how to know the best statistical method to use depending on the kind of data you're working with, whether your data is cross-sectional, your data is longitudinal. What do we mean by cross-sectional data? What do you mean by longitudinal data? All those kind of things, you'll be able to find them there. And then the type of regression models we have depend on the nature of the outcome variable and so on and so forth. So it meant that if you want to understand the theory bit, you can get that information there just looking at introductory statistics sessions. And then if it's about power analysis, you want to know how to power your study, then there's a whole video, the whole series on power analysis using G-Power software, which is also there. And then if it's about, for instance, even how to use Mendeley and Quillbot, that has nothing to do with statistics. It is also covered there. And then, so for instance, regression modeling, another inferential test has been covered. The most important information you need to know in statistics. And then now you notice that what I'm using is different from the classical R software you are aware of, right? So I'll explain the difference. But so what I'm using is called Jupyter Notebook. So with the Jupyter Notebook, you can clearly see that I can even insert pictures. I can insert links. I can also produce all my codes in there, all my R codes in there, and all the graphs will come just beneath it. So it means that anything I do, so if I import a data, everything is just beneath it. I don't need to go in. So you notice that in every other software you've been using, most of the time, you have to now save your outputs in a different file, right? But with the help of the Jupyter Notebook, you don't have to do that. And the beauty is that you can download the file as an executable script. The executable script will be similar as if you had done it in RStudio. Okay, so I was going to talk about IDE later on. And so at this stage, I don't expect you to understand what I mean by RStudio or IDE because it's something I was going to talk on. But the beauty is that you can download your script as if you had done it in IDE. If, let's say, especially those who are doing their PhDs or those who have been meeting supervisors, you don't need to be doing your analysis in just RStudio, and then you have to now save your output separately. Or if you are doing it in SPSS or Stata, you produce your graphs, then you copy and paste into Word, and that's all a bit stressful. And at the end of the day, you might even forget which line of code produce a particular output. So with the help of this, and I can also download it as an HTML file. So if I download it as an HTML file, what that means is that when you go to your downloads, so in this case, if I go to my downloads, it has been downloaded as HTML, but the previous one was downloaded as R. So for the HTML file, what that means is that you will get it exactly like the Jupyter Notebook, just that now you can't edit the code, but you can copy it into your RStudio. Okay, it means you have access to everything, just like read only, and all the links are clickable. Everything is still clickable. Yeah. So that's the beauty about the Jupyter Notebook. So I would say by far it's the best, and it can run different programming languages at the same time. So at the moment I am using R, but naturally it was done it was by default, it makes use of Python. So here it is making use of Python. If I want to use R, then I have to switch the kernel to R. And if I wanted to do C++ and other programming languages, I just needed to add that kernel to that to this, and I can run those programming softwares as well, or languages as well. Okay. All right. So so basically, this is just to say that on the channel, it depends on what you are looking for. So if you want to get a good understanding about statistics, a good understanding about how to know the right statistical method for the right job, that is a good place to start, is to go through quantitative methods for research and all the recent videos that I've done, because I've recently done similar sessions with other student buddies. So, for instance, mastering feature selection, unlocking complex research, introduction to analysis and forensic insight, and all those things. Yeah. So, please, it looks like there's can you please mute everyone, please? Hello. Okay. Please, can you hear me?
Yes, please.
Yes, we
Hello.
can hear you, Doctor. Sorry about the feedback.
Yeah, I can hear you.
No worries. All right. So basically, what this is to say that when you go to the channel, it depends on what you want. If it's about programming from scratch, then you start with the first video. Okay, then you progress. And then the Jupyter Notebook I was just talking about, there's a whole video on how to switch from RStudio to Jupyter Notebook. So you can also watch that. And I'm sure by the end of today's meeting, you fall in love with Jupyter Notebook. That is actually what I've been using for all my previous sessions with Nuxa China and all the other, because it makes teaching quite handy and easy. So that's why I make use of that. Yeah. So, and there are so many intro to statistics on the channel, including advanced methods. So when you just go there, you just explore. So I would advise that you probably start with the introduction to statistics. I did these 4 was done for Oxford University students and staff. So you can start with that. And then recently I did one for another student buddy. I think that's empowering women researchers in STEM. So all the videos on empowering women researchers in STEM is just similar to like it was a master class, and just that we also learned how to use statistics to solve a forensic research, which was quite interesting. Like imagine you are using statistics to help us to determine the kind of weapon that was used to cause and inflict some wounds on some individuals that we didn't know anything about. Yeah, so it's quite interesting. So there are so many interesting stuff there. All right. So now coming back to what we are going to do today. So like I said, just a quick recap is that we are going to I'm going to talk a bit about some of the advanced statistical methods and a brief introduction to the statistical programming, and then we'll look a bit into some practice tasks. But the practice task, it appears, I'll just give a brief intro. I couldn't wrap up all the codes because I was time bound. So we'll see what we can do when we get there. So for the generalized linear models, it's basically just regression models that are applied to cross-sectional data sets. So remember that when you talk about data structure, so there are 2 types of data structure. So it means that when you're going to do analysis and you want to know the kind of statistical methods you should use, especially when we talk about regression, there are 2 important things. One is to know the nature of the data structure, and also the nature of the dependent variable. So it means that for regression, we have some dependent variable or some outcome variable that we want to see certain factors that predict it. Okay, so it means that for regression, we are always looking at a one-dimensional association of some set of predictors on that outcome. Okay, so when I mean by a one-dimensional, it means that it's just a straight line. So that's what I mean by one-dimensional. It can be more complex. Okay, but the emphasis is we apply it to cross-sectional data. So the question is, what's a cross-sectional data? Anytime you have a data with several variables, and each row of the data correspond to a particular subject or individual, meaning that each individual has only one row in the data. That is a cross-sectional data. It means that those data where we didn't follow an individual over time, then it becomes a cross-sectional. It doesn't have to be only about humans. It could even be about just any data where for each ID, the ID could be about humans, it could be about any subject. Once the ID, each ID has just one row of the data, then that makes it cross-sectional. And for cross-sectional data sets, the regression models that we apply on the cross-sectional data set are called fixed effect regression models. And now for those fixed effect regression models, that's why we are calling it as generalized linear models. So it means for the generalized linear models, it is also considered as fixed effect regression models. And remember that they are fixed effect because it's applied to only cross-sectional data sets. Fine. Now, so it means that in order to determine the choice of model, even for the generalized linear model, the first thing is the data structure. If the data structure is not cross-sectional, but rather longitudinal in the sense that a particular individual could be followed at multiple time points, or a particular individual would have multiple rows of data in the same data set, then that's a cross-sectional data. Others call it panel data. So if you hear of panel data, it's the same thing as cross-sectional, longitudinal data, sorry. And so for the longitudinal data set, those are, if you want to model longitudinal data set, then you need to use something called mixed effect regression model. So that is the second part. So the mixed effect models is just the same generalized linear models, but applying it to longitudinal data sets. Okay, so for the generalized linear models, now we've learned that either the mixed effect or the general linear models, they are two, how do you call it? They are two important information you need to know. One is the nature of the data structure, and then the next one is the nature of the outcome variable. So please, if you have questions, what I'll advise is that rather maybe save the question, just write it down, and then at a point I would let me finish the first phase. Now we have like 3 phases. So let me finish the first phase, then I'll take questions. Then we'll go to the second phase and the third phase. Yeah. So that I can answer all your questions. Fine. So for the generalized linear models, like I said, apart from the data structure, the next thing is the nature of the dependent variable, not the nature of the predictors. So the predictors could be continuous, could be disparate, it could be categorical. We don't care. It's rather the dependent variable. If the dependent variable is categorical, it introduces some class of models called logistic regression models. And if the categories are just 2, that's a binary or binomial logistic. And if the categories are more than 2, that is 3 or more, then we have a multinomial logistic regression model. Even with that, we could also have situations where the categories have natural ranking in there. Like, let's say if you are talking about grades of infection, where we could have grade 1, grade 2, grade 3. It's categorical, but there's some ranking in there. That introduces something called ordinal logistic regression. And then the logistic models estimates odds ratios, but there are instances where you are interested in estimating risk ratios. So there's another class of model called log binomial regression. So the log binomial regression is synonymous to the logistic regression, but it is used to estimate risk ratios, especially situations where you are rather interested in quantifying the risk and not the likelihood of experiencing an event. So the likelihood of experiencing an event can be quantified based on the odds ratios, but the risk ratios would help you to rather quantify the risk. Okay, so that is one thing you should note. And then if the dependent variable is continuous, it introduces us to some class of models. We have the OLS regression, ordinary least square regression. We have generalized least square. We have quantile regression and COVA, and so on and so forth. And if the dependent variable is count or discrete in nature, then it introduces us to some class of models called Poisson class of models. And for Poisson, it has some parametric assumption that the conditional mean and variance of the outcome should be equal. If it is not equal, then it means there's dispersion in the data. If the mean is greater than the variance, it introduces over dispersion, and if it's less, under dispersion. And in the case of dispersion, when the mean and variance are not equal, then quasi-Poisson and negative binomial regression becomes the next alternatives. So this is just to say that even for the fixed effect regression models, where the data is cross-sectional, the nature of the dependent variable, whether continuous, discrete, or count, that continuous, discrete, or categorical, introduces the class or tells the choice of models you can use. And if the data is cross-sectional, so it means once you are given a data and you want to do regression, don't just go ahead doing the regression without first of all knowing the structure of the data, whether it's cross-sectional or longitudinal. Remember, if you apply cross-sectional data, if you apply fixed effect regression models to a longitudinal data set, it means the data set was longitudinal, but you are assuming it is cross-sectional. That is wrong. So it means that anytime you mistakenly use a fixed effect, let's say Poisson regression, to model, let's say, number of road accident factors predicting number of road accidents in, let's say, in a certain country, right? In that case, remember that you are telling the model that even though the data is cross-sectional, where individuals have multiple rows in the data, you are telling it that it should assume that each row of the data corresponds to a different individual. So it means that it is going to be a statistical suicide if you apply fixed effect regression models to what? To longitudinal data set. Fine. Now, I just talked about, and this thing I've already touched comprehensively on my YouTube channel. Now, when you talk about the longitudinal data set, there's also another data structure I want you to note. So it is not all the time that data is what? Data. So remember, when you talk about cross-sectional, we are saying that each individual has what? A single row of the data, right? A single row in the data. That's fine. But you notice that what makes it cross-sectional is also that we are collecting several information at the same time. Okay. And we have even different types of cross-sectional. We also have something called pooled cross-sectional. So if you go to the YouTube channel, I think I've covered that extensively. So I don't want to go much into that because that's like a whole lecture. Who is writing on that? I don't know how this thing came up on. Is it possible the person could erase it or something? Okay, it's fine. I think I should be able to erase it from here. Okay. All right. So, can you hear me, please?
Loud and clear,
Yes,
sir.
please.
Yeah, we can hear you.
All right, thank you.
You
Okay,
are
so
very good.
okay, that's fine. So now for the mixed effect models, okay. So the mixed effect models, remember that it is used to model two things, two kind of data structure. One is longitudinal data, and two is the hierarchical data set. Okay, hierarchical data set. So what is hierarchical or nested data? So you notice that, so for instance, let's say you are collecting data on patients, where each different set of patients or some set of patients were taken care of by a particular doctor. So you have a variable called doctor ID, where let's say if the patient are about 600, about 100 of them were taken care for by a particular doctor. So we have that kind of data. And let's say if these patients were also selected from different district hospitals or different hospitals. So it means patients are clustered under doctors, and then they are also clustered under hospitals. So that's like an example of a hierarchical or nested data set. So it means that a nested data, you can think of a nested data as situations where we have hierarchies in the data set, such that you have the subject, and the subject too can be classified into, let's say, if it's about, how do you call it? Even populations and census and so on and so forth. You notice that we have citizens or individuals, and the individuals might belong to some specific communities or towns, and the towns might be nested under different districts. District might be nested under different regions. Regions might be nested under something else. Yeah, and so that's like a typical example of hierarchical data set. So it means another name for mixed effect model is also hierarchical linear models or hierarchical linear regression. And another name is multi-level regression. So if you hear multi-level regression, it's the same thing as hierarchical linear regression. Now, there is something I want people to be aware of. There is something called hierarchical regression, and there's something called hierarchical linear regression. So the one without the linear component is actually situations where, let's say you have, I've already covered that on the YouTube channel. I think if you watch this video, I think, yes, this video. So if you watch this video, you know that the distinction between that. But basically, there are instances where you have, let's say, 5 predictors, and you want to see how they predict the outcome. But instead of putting all the variables, the predictors in the model and fitting it just like we often do, you want to do it in a stepwise fashion. So you first of all put the first predictor in the model, you fit the model, and then you put the second one into the model. So meaning there's already a variable, a predictor in the model. You put the second one, and there are instances where the previous predictor was not significant, but after adding the second one, it made it to be significant. It means that new variable could be a potential mediator. So it means the hierarchical regression is a way of identifying potential mediators or moderators. I don't expect you to understand the mediators and moderators now. I think I'll talk about it a bit, but again, I've already covered that as well. So if you watch, I think one of either this video or that video, the part B of this introductory session 2, or the part A, I think I've covered that extensively there. So for the how do you call it? So for the hierarchical data, so this is just data which is nested, okay, nested within itself, and so it means there are high level nested levels, okay, in that data, and then so it means we can have a data which is nested and also collected over time. So you could have a longitudinal, hierarchical, or nested data. Again, the mixed effect model can handle that. So with the previous hierarchical regression as a model selection or as a model fitting criteria, I think what I was trying to explain was that you don't put all the variables, the predictors in the model at the same time. You do that in a stepwise fashion, and at each stage you evaluate the model and the R square. And then when you add the new one, you check whether the change in R square was significant or not. If it wasn't significant, then it meant that the new addition did not improve the model. I'm not talking about whether it increased the variable, the R square, because if you have a model with one predictor, if you add a second one, automatically the R square will increase, even if the second predictor is significant or not. However, if the change in R square is significant, then it meant that the new variable was a significant improvement of the model. And so with that, it helps us to identify potential mediators. So a mediator is a situation where a certain predictor was not significant or they didn't have significant effect on the outcome, but in the presence of another variable, it became significant. So it means that variable does not have a direct effect on the outcome, but it has an indirect effect or indirect significance in the presence of a certain third variable. And that third variable is a potential mediator. And there's something called moderators. So moderators are situations where you have, let's say, some predictor has an association or an effect on the outcome. The effect could be positive effect or negative effect. And then in the presence of a third variable, that association either increases or decreases, or the direction of association could also change. So it means there are situations where in the hierarchical fashion, you added the first predictor into the model, which had a negative effect on the outcome. But after adding a third variable as the next step, it caused the variable which was positively and negatively related to the outcome to become positive, or it caused the R squared to significantly increase. So it means that in that case, that third variable has increased the strength of association. Or let's say if it rather decreased the R squared, then it means that it has also decreased the strength of association. So moderators either decrease or increase the strength of association between a predictor and the outcome, or it could also change the course or the direction of association. So, and that's why people use hierarchical regression, the one without the linear aspect. Okay, so remember, hierarchical linear regression is the same thing as mixed effect models, but without the linear wording. That hierarchical regression is just like a stepwise regression. Okay, it's like a stepwise regression. But that one is often employed when you want to explore much more complex dynamics of the association, identifying potential moderators and mediators. If something is found as potential moderator mediator, you can now do a proper moderation mediation analysis to check that. When you combine hierarchical linear regression, when you combine that hierarchical or stepwise regression with a moderation mediation analysis, then you don't need to do anything about structural equation modeling. So structural equation modeling, mostly before people do structural equation modeling, and we are going to talk about that later on, and you are not even sure about the kind of structure, you can use hierarchical regression. That's that hierarchical stepwise regression. Let me use stepwise in there, that so that it makes it easier. So hierarchical stepwise regression. If you couple that with moderation mediation analysis, you'll be able to identify any hypothesis, any complex hypothesis or relationship you want to investigate without even having to use structural equation models. But those who use structural equation models, when they are not too sure about the kind of structure or hypothesis they want to test, they use the hierarchical linear regression coupled with moderation mediation analysis as a preliminary analysis before the structural equation modeling. So this is just something I wanted you to know. So don't confuse hierarchical linear regression with hierarchical stepwise regression. They are two different things. So the hierarchical linear regression or the multi-level regression is the same thing as mixed effect models. And we said mixed effect models can be used to model either a data which is longitudinal in time, or two, a data which is nested in time, nested in terms of nested or hierarchical levels, and also a data which is nested, but also collected over time, right? So that's basically, so it means that the mixed effect model is a generalization. So anytime you want to do repeated measures, like a data where the dependent variable 2 has multiple time points, so that's a perfect example of a longitudinal case. So it means all repeated measures data can also be modeled with mixed effect regression model. So anytime you want to do repeated measures ANOVA, remember you can also use mixed effect regression for that by treating the multiple time points as a random effect, and then if you are trying to compare that between some groups, then you put the group as a predictor in the model, and then the outcome variable is the dependent variable, and so on. So for mixed effect models, it has two things that you need to be aware of. So we have the fixed effect and the random effect. So those two combines to form what we mean by mixed effect. The first phase, we said the generalized linear models is just fixed effect models that is applied to just cross-sectional data, right? Now for the mixed effect, we are saying that mixed effect has two components. We have the fixed effect and the mixed effect. The fixed effect are those predictors of interest. So it means that predictors of interest will automatically be considered as fixed effect. And then the random effect variables, they are the variables that talk about the structure of the data. So it means the random effect variables, they are the variables that are not predictors of interest, but they talk about the structure of the data. By talking about the structure of the data means that there are variability in the data set, and those variability in the data set are due to those variables. So for instance, if data is collected over time, it is collected over time because we believe that the data might change with time. So it means time adds some variability or variations to the data. So in that case, even though time is not a predictor of interest, I have to add time as a random effect to account for the temporal pseudo replication or the temporal effect in the data. Okay, so in that case, you add time as a random effect. And they are also so in this case, when they are those variables that are the high order hierarchies. So if you have doctors, if you have, let's say, patient nested under doctors, they will put doctors as the doctor ID as a random effect, even because it's not a predictor, but it tells that the patient were clustered or nested under doctors. So in that case, you have to add that as a random effect. Okay, so it means that, and not just that, anything. So for instance, spatial replication. Imagine if we're collecting data at some specific locations over time, then it means there could be spatial effect. This is to say that the data you are going to see at a particular location might vary from one location to the other. So it means location is contributing to some variability to the data. And any source of variability, any variable that is contributing to any source of variability, is a potential what? Random effect variable. Okay, and that is just talking about the structure of the data. So that is how robust mixed effect models are to modeling both longitudinal data sets and then hierarchical data sets, or both. All right, and the last one is what we've been collecting data and we add patient ID or subject ID. Would you believe that if you add patient ID as a random effect, it is trying to do something very magnificent? So, for instance, if you add patient ID as a random effect, it accounts for something you call individual heterogeneity. This is to say, situations where, let's say, you are trying to predict some outcome, okay, but you believe that the patient can be very different. Maybe the differences you are seeing could be due to the fact that they have different immune response. They have different, there are some external variables or external factors that are contributing to certain variability in the data that we don't know about. So adding patient ID as a random effect is trying to tell the model that it should treat each patient as different. This is to say that it should assume that there's some external factors that are also accounting for additional variability across patient or between patients. So it should treat it as such. Okay, so that's also one of the beauties about adding patient ID as a mixed effect, as a random effect in the model. So that is all about the mixed effect models. So the mixed effect models is the same generalized linear model. So all the generalized linear models I mentioned here about the logistic models, the Poisson class of models, the OLS class of models is the same thing, but this time around you are applying it to a longitudinal or a nested data set. And that and then in R, there are specific functions to perform that. So if you want to do anything now, we are in the global world. ChatGPT is there, and you can even go to Google. If once you're able to import data into R, you don't even need anyone to help you. The rest is just making use of online resources, and you'll be fine. Okay, so that's it. Every good programmer, you don't have to stress yourself if someone has already developed a package to do something. Okay, it's only when you are learning how programming skills. So for instance, on the YouTube channel, you see like a video on creating complex functions in R, like how to write your own functions in R. That sometimes is very useful, especially those who are doing your PhDs, doing simulations, those who are doing complex stuff that there are no packages for. You should be able to write your own functions to do certain things. Even in this particular, when you get to the practice session, you notice that I had to write my own functions to do certain things that there are no existing packages for. Sometimes by making use of existing packages to still modify or create your own functions as well. All right, so this is the first two class of models I want you to know. So these two are regression model, okay? So I want you to note that. But there's a disclaimer I have to give. So most people from non-statistical backgrounds usually confuse multivariate regression with multiple regression. So let's try and understand the difference. So one thing is this: anytime we have a single predictor, and then a single outcome. So let's assume that the outcomes are just single, just one dependent variable you want to predict. Okay, for instance, you want to predict infection status. You want to predict, let's say, immune response. You want to predict student performance based on their GPA and so on. So just a single one. So now we are assuming single dependent variable. The moment the predictor is just one predictor, that is what we call a simple regression. So whenever you hear simple means that there was only one predictor. But the moment there are more than one predictors in the model where the outcome is just one, that is what we mean by multiple regression. So you can call it multiple linear regression because the model is a linear model. We could have a non-linear model, situations where you believe that the variables have non-linear effect on the outcome. Then in that case, you can have non-linear or polynomial regression models. Those also exist. Okay, there are instances where you are still using a linear model, but there's a particular variable that has a non-linear relationship with the outcome. So maybe it has a quadratic relationship with the outcome after you did a scatter plot. So in that case, one could decide to add a quadratic term to the model, and it's still a linear model with a quadratic term, fine. But that's not what I'm trying to talk about. What I'm trying to say is that let's assume we are using linear models. So for the linear models, situations where you have more than one predictor in the model. That is what we mean by a multiple regression. The moment you hear multivariate regression, it means that there are more than one dependent variable. So multivariate applies to the dependent variable, whilst multiple and simple applies to the predictors or the independent variable. So it means I could have a multivariate simple regression. So a multivariate simple regression will be a regression model which has several dependent variables, but only one predictor. So that's a multivariate simple regression. So I could have a multivariate multiple regression where we have several dependent variables and several predictors. Okay, so these are something I want people to understand, especially when you talk about survival analysis. We'll get to that point, and I'll tell you the mistakes people have been making about calling something multivariate survival analysis, which is very wrong. They meant to say multiple. Another best way to call multiple is multivariable. So if you don't want a problem, you could call it multivariable regression or multiple regression. Multivariable seems to be like a better wording in situations where you feel like multiple doesn't look too much sounding, especially when they talk about survival analysis. So we'll come there. So again, at this phase of the presentation, we are just introducing some of the existing modern statistical methods out there and when and how to use them. All right. So the next one is there are a class of models called machine learning methods. Okay. So I'm sure most people have probably heard about it in recent times. So deep learning and we have machine learning. They are a bit distinct but similar. And remember that when you talk about machine learning, one thing I want you to notice that it depends on the area of application. Depending on the area of application, the class of machine learning methods will be different. So it means if you are talking about time series analysis, we have machine learning methods specifically for time series analysis. If you are talking about facial recognition, voice recognition, how to depending on certain characteristics of an individual, you want to be able to determine whether that individual is so for instance, let's say if you have captured your face, okay, and then you are, especially when you are going through the airport or anywhere they apply facial recognition algorithms. The whole point is underneath those algorithms are machine learning techniques going on there, okay, or deep learning methods and underpinning those algorithms, such that it's helping us to predict if you are indeed that individual or not, right? So I'm just trying to say that the class of machine learning I'll use for classification problems will be different from the class of machine learning method I'll use for facial recognition or voice recognition or even natural language processing. They'll be different. Okay, so I'm just trying to say that machine learning methods are very wide and it depends on the area of application. Okay, fine. But when it comes to regression, all the regression models you've mentioned, okay, the generalized linear models we've mentioned, we have its machine learning equivalent. So for instance, classification tree and decision tree, they are the basic machine learning regression methods, okay? So what they do is that they fit models, but present models in a form of a tree structure. So it means unlike the classical generalized linear models or the generalized linear mixed models, okay, the generalized linear mixed models are also the mixed effect models, okay, and we just learned that they are also known as multi-level models or hierarchical linear regression. And the hierarchical linear regression is different from hierarchical stepwise regression. We've learned that. Fine. Now, for every generalized linear model here, we have its equivalent machine learning technique. So classification tree is where the dependent variable is what? Categorical. And then we have decision tree where the dependent variable is either continuous or discrete. So in that case, it allows you to choose the error distribution, whether Poisson or whether continuous. Okay, fine. So mostly continuous are Gaussian. Fine. So it means that we have classification tree and we have random forest, gradient boosting machines, support vector machines, and so on. So these variables are also able to model much more complex relationship, including nonlinear effect. Remember, with the generalized linear models or the generalized linear mixed effect models, naturally, we expect each of the predictors to have a linear relationship on the outcome. But in real life, it is not always the time. That is why sometimes some of the regression model fails to satisfy certain parametric assumptions. So this is to say that situations where a particular continuous predictor has a nonlinear effect on the outcome after you did a scatter plot, okay, you realize that the relationship between a particular continuous predictor and, let's say, a continuous outcome variable was a bit nonlinear, then what other researchers tend to do is that they fit something called splines to those predictors with nonlinear relationship on the outcome to smoothen out that nonlinear effect to make it fairly linear. And that alone introduces another class of regression models called generalized additive models. So it means the generalized additive models, we have the fixed effect and the mixed effect. So you could have generalized additive mixed models, or if you just hear generalized additive models, that's the fixed effect. So the generalized additive mixed models, or the generalized additive models, is just the same GLMs we've talked about and the GLMM we've talked about. However, the only difference is that it is allowing us to fit splines to those predictors that have nonlinear relationship on the outcome. So that is another alternative to nonlinear regression. Okay. So it means that instead of me using nonlinear regression, I'm imposing a linear effect on that variable with nonlinear association on the outcome by fitting splines to it. Example of such splines, we call one of the examples is these splines, and it will smoothen out the nonlinearity to make that variable, the transform variable, to be fairly linear on the outcome. And then you can now predict, because remember that the linear regression is assuming each of the predictors have a linear relationship on the outcome. If that is not the case, you have to now think about an alternative. So machine learning is just state-of-the-art methods that are used to that applies deep learning techniques and machine learning techniques to also perform these class of regression models. And like I've already given a disclaimer that the choice of machine learning methods will depend on the area of application. For time series, so for instance, let me see. So for time series, I thought I added a paper to it. So for instance, let me just go to Google Scholar. So let me type, okay, fine. So so this is like one of my publications where which is published in one of the top K1 journals in forecasting. Okay, so here you learn that we're using machine learning techniques for forecasting and backward prediction in time. Okay, and it was first of its kind. It's quite a bit mathematical heavy, but not very yeah. So you notice that the class of models outlined there, you can't use it for regression. It's just for time series. Okay, so that's basically what I'm trying to explain with the difference. Okay. Now, the next one I just want you to talk about, for us to talk about, a survival analysis. And today's practice task was going to be based on that. Yeah, so for survival analysis, this is used to model time to event outcomes. So situations where, let's say, especially those in medicine, we use that a lot. Those into clinical trials, they use that a lot. So for instance, let's say situations where you are looking at the time to an individual dying from an infection, or maybe the time to an individual experiencing an adverse event in a study, or the time to an individual withdrawing from something. So it's just, or time to relapse, okay, or time to remission. So so it means that anytime you are looking at time to event outcomes, remember we often call it survival analysis, okay, or sometimes the data, we call it survival data. But remember that it is only because the original, the whoever developed survival analysis for the first time was applying it to an outcome which was time to survival. So ever since the person who developed these class of models applied it to an outcome which was time to survival, it has now made it somehow get the name survival analysis. But sometimes I'm just trying to say that it doesn't mean that it is only used for only studies that are about survival. No, it could even be time to a machine breaking down. Okay, so that's why the better wording should be time to event analysis. That would be like a generalization, so that survival analysis will just be a subset of it. But unfortunately, whoever developed the method applied it to survival, time to survival, and that's why it picked that name. So with that, we have something called Kaplan-Meier analysis, which is a non-parametric analysis. Which is a non-parametric analysis. So what it does is that it's a univariate analysis. This is to say that for Kaplan-Meier situations where you want to visualize survival curves, okay, between some categories, okay. So it means that if, let's say, I'm looking at time to survival or time to death, okay, and I'm comparing the time to death between males and females, then I'll have a certain nice survival curves stratifying it or distinguishing between males and females. And that kind of graph or those survival curves are obtained from what we call Kaplan-Meier analysis. And they are univariate because you can only look at one categorical predictor at a time. You cannot apply Kaplan-Meier to a continuous predictor. Before you will be able to apply to a continuous predictor, you have to categorize the continuous predictor in order to use Kaplan-Meier analysis on that. Now there's an extension. So here, like you said, you notice I said univariate. Okay, univariate is a univariate survival method because it's only considering. So remember, at this stage, the outcome variable is just one time to event outcomes. Okay, just one time to event outcome. So it is only one dependent variable. So it's univariate. But here, I'm using the univariate also to refer to the fact that it has only one predictor at a particular point in time. And then we decided now to extend that, and it gives rise to a semi-parametric method called Cox proportional hazard models. Okay, so the Cox proportional hazard model is a regression model. Okay, it's a regression model, just that the outcome variable is a time to event outcome. And with that, you can now look at several predictors, how several predictors predict the outcome. Okay, fine. Now, for the Cox proportional hazard model, it is used to estimate hazard ratios. Okay, and there's a parametric assumption. There's a particular strong assumption that needs to be identified. So there is something called a proportional, just as you said, as the name goes, Cox proportional hazard. So it means the hazard ratios or the hazard must be constant. But the moment the constant hazard or proportional hazard assumption is violated, we have other methods that we use. Fine. But here, the disclaimer is that most biologists or clinicians call the Cox proportional hazard models as multivariate survival models, which is very wrong. Okay, it's not multivariate survival model. They are calling it multivariate because they are confusing it with multiple regression. Like I said, multiple means several predictors. But because the Cox proportional hazard allows you to look at several predictors on the outcome, they are calling it rather multivariate regression. It is not. Rather call it a multivariable survival model. In that case, you don't have any problem. So call it a multivariable survival model. If you call it multiple survival model, maybe it will look a bit ambiguous. So rather call it multivariable survival model, but don't call it multivariate. The moment you tell me multivariate survival model, you are trying to tell me that you are jointly modeling two time to event outcomes, two or more time to event outcomes. And currently we don't have existing methods to do that. Okay, so there's nothing like multivariate survival models at this stage, but we have a multivariable survival models. And there's an extension called multi-state Markov models, I also have like a paper that involved or employed the multi-state Markov model. It's in a Springer Nature journal. And so I will explain briefly what the multi-state Markov model does. So the multi-state Markov model is just a generalization of the standard survival models. So anytime you hear standard survival models, we are talking about Kaplan-Meier and the Cox proportional hazard models. For Kaplan-Meier, once you get the survival curves between the categorical predictors, okay, you can check whether there's significant difference in the survival curves. And the popular test we use is called log rank test, which is a popular test that we often use for that. Okay, so don't do Kaplan-Meier analysis without a log rank test. Okay, because remember, we can't make inference based on descriptive statistics. So it means that once you produce a graph for me, or you produce central tendencies, the mean, median, mode, and those things, you cannot make an inference from it. Okay, you cannot say that because the survival curve of males appears to be higher than females, then it means there's a significant difference. No, you cannot talk about significant difference as far as until you do a statistical test. And that's what we mean by inferential statistics. So statistics is broadly classified into descriptive statistics and inferential. For the descriptive, it's just to summarize the data, either graphically or by certain summary measures, okay? But if you want to now make an inference or a conclusion with confidence, that confidence is quantified by confidence levels, and that introduces what we mean by inferential statistics. So all the regression tests, all the statistical hypothesis tests, and then all the statistical models collectively are what we call inferential statistical models, or inferential statistical or inferential statistics, basically. All right. So anytime you hear inferential statistics or inferential statistical methods, we mean statistical tests and statistical models. And for statistical tests and statistical models, they are different. For regression, it's a model because there are certain unknown parameters that we need to estimate. ANOVA or t-test is not a model. It is rather used to just test the validity of some hypothesis. So it means that whenever we are talking about hypothesis testing, we don't estimate any parameters. So that is why that is called test. And then for models, we estimate parameters. And that is why it's called what? A model. So it means that don't confuse statistical tests with statistical models as well. All right. And so with this classical survival analysis, you notice that it has a certain weak assumption. So for instance, let's say if you're talking about time to death. If time to death is the dependent variable, okay, for our survival analysis. Now look at this. You notice that there are situations where an individual, okay, who entered the study can undergo different possible transitions before death eventually occurs. So for instance, an individual could be healthy and later on get a mild infection and later on transition into a severe infection, but someone at severe after some future time can maybe come back to mild, and someone can even at mild can become healthy, and someone from healthy can go back to mild infection, and from mild can go back to, let's say, severe infection and eventually die. But the standard survival models ignore those history. It only looks at the end of the study, was the individual dead or alive? So it means it throws away all the information about possible disease transitions that an individual actually make over the course of their infection or before death eventually occurred. So the multi-state Markov model extends these traditional models by capturing those possible transitions that occurs. And this particular paper of mine was applying that to how do you call it? Was applying that to where is it? Okay, was applying that to a biological data. Okay, so I mean you can take time and go through that. Yeah, but today the goal was to develop a code for that to a medical application problem we wanted to solve together. I always like to wrap my sessions with an application and in R, and always it's not just any application, but something meaningful that you could also even base on it and develop research problems and research topics and so on. But unfortunately, time couldn't permit me to wrap up or finish up the course because I was a bit lazy, and I'm sorry, but I'll see what I can do. The course for this one is, I think, is online, but I'll see what to do. All right. So basically, that is one thing I wanted you to note about the multi-state Markov model. And remember that sometimes, let's say, now every time people are doing research and people want to publish high impact publications, but would you believe that if you know and understand a certain statistical model, you can base on that model to design a study, and that study will be novel for the first time in your area. Multi-state Markov model is underused. Many people don't even know about it. But the truth is that it is the most realistic way to model a survival data. Okay, like I said, the classical ones ignore all the possible transitions that occurs. And we'll look at an example during the practice session. Okay, so the next one is structural equation modeling. I won't talk much about it because I've already covered it on my YouTube channel. But you notice that for generalized linear models, the generalized linear models, I can call it fixed effect linear models, okay, because I said they are fixed effect because the data is just cross-sectional. Okay, and then the mixed effect I've already explained it, fine. Now, these regression models, even including machine learning regression models, is assuming that the dependent variable, okay, It's assuming that the dependent variable has a one-dimensional association on the outcome. But now look at this. Let's look at this example. Now, so the code here, it means that you can use R to create conceptual frameworks. So that's one thing I wanted you to note. So for instance, so that's, you see, if you look at the Jupyter notebook, you notice that all these are programming codes I've been doing. And I don't need to go and save it in a separate folder somewhere. It manages, it tells me that anytime I want to retrieve anything, I just click on what I'm interested in and I get back all the codes and everything fine. So for instance, I used the how do you call it? R, okay, to construct this conceptual framework. I didn't have to do it in PowerPoint. Okay, so I'm just trying to say that R is that powerful and you can use it for anything you want. Just search for it if you want to know how to do that. Okay, fine. So now here, now let's look at, so in a one-dimensional case, I was going to look at how, let's say, psychological well-being, work engagement, and let's say job satisfaction predict, let's say, burnout. Okay, if burnout is an outcome. In that case, it's just a one-dimensional association or the one-dimensional effect of these predictors on the outcome. But situations where I want to now explore much more complex, much more complex associations in order to answer multiple hypotheses at the same time. So for instance, here I could have multiple hypotheses. Like I want to know whether, so for instance, here I'm looking at whether job satisfaction mediates the relationship between work engagement and burnout. By mediating means that in the presence of job satisfaction, work engagement would have a positive, would have an association with burnout outcome. In its absence, it will not. So that's what we mean by a mediator. Okay. And there is, and I think I've explained what a moderator is. So for moderators, they either increase the strength of and direction of association. Okay. They either increase or change the direction of association. Okay, fine. Okay, so that's basically that. So what we use structural equation modeling for is to now investigate much more complex or extend the classical one-dimensional association to multiple ones. And the beauty is that you could even model or have more than one dependent variable in the same structure. So for instance, here I have two different dependent variables. But if you want to now model two different dependent variables, especially for the fixed effect models, we have existing methods called multivariate regression. So it means the multivariate regression allows you to model. So for instance, situations where you are looking at some set of predictors, how they predict a certain outcome, and you are using the same set of predictors. You want to know how that same set of predictors predict another outcome variable. You don't have to do it separately. You can combine it using the multivariate regression. So multivariate regression would literally fit separate regression model and account for the relationship between the two dependent variables. If the dependent variables are even three, so it means you are looking at the effect of the same set of predictors on three different outcomes or three different dependent variables, then it means that the multivariate regression will fit different regression models and also account for the relationship between the dependent variables. Okay, but if you fit separate ones, okay, so meaning that if you use, let's say, a different model for each of the outcomes, you didn't account for the relationship or the associations between or the correlation between the dependent variables, and somehow it can affect the estimate, especially if you are looking at the same set of predictors on those outcomes. So as a matter of fact, that tells us that even when it comes to hypothesis testing, where you want to do t-test or you want to do ANOVA, you notice that for ANOVA, you have a particular continuous variable and you want to see how that continuous variable differs between three or more groups. What if you have more than one of that continuous variable? Let's say you have about three different continuous variables or three different outcome variables, and you want to see how each of them differs between three or more groups. You don't have to do separate ANOVAs. You have to first of all do something called a multivariate ANOVA, and that multivariate ANOVA is called MANOVA. So when you do the MANOVA, and MANOVA concludes on significant difference, then it means that at least one of those predictors was significantly different. then you can now go and do the separate ANOVAs. But imagine if you do multivariate ANOVA and it says that there's no difference. Sometimes it can save you fortune or time, especially those who are into bioinformatics or those who do a lot of proteomics data analysis or genomic data analysis and so on. You notice that there are instances where you have so many protein expressions, or let's say so many variables, not just, sometimes it could be about 500, 300, and you wanted to do separate ANOVAs for each of them. That is too much. So what that means is that imagine if you do that multivariate analysis and it concludes that there's no difference, okay, at the multivariate level between the three or more groups, then it saves you time. You don't have to now do any how do you call it, individual ANOVAs or separate ANOVAs in that instance. Okay, so that's one of the advantage of doing that. It's just like you trying to do pairwise comparison after you do ANOVA. If ANOVA concludes there's a difference, that is the only instance you now have to do that pairwise comparison. But if ANOVA concludes there's no difference between three or more groups, it means that if you even do pairwise comparison, you not see any difference between any pair. Okay, so it means once the ANOVA is not significant, then there's no need for pairwise comparison. The same thing when multivariate ANOVA is not significant, then there's no need to do separate ANOVAs, because it means that none of the separate ANOVAs will be significant, even if you do it. Okay, so that's one of the things I wanted you to know. But for structural equation model, you can even model 3 or more outcomes at the same time and look at complex associations and so on and so forth. And before you do structural equation modeling, remember, you can apply the hierarchical stepwise regression and the moderation mediation analysis as an alternative. Or people can do that first before they do that, especially if you don't even know how this structure should be like. So you can use the hierarchical regression, stepwise regression, and then the moderation mediation analysis. A typical example is something called Anderson-Hayes moderation and mediation analysis test. You can read about it. Anderson-Hayes. How do I spell it? So it's Anderson. Anderson-Hayes, especially those who use SPSS. There's a micro, an external software that allows you to add that particular test into SPSS. But R also has the micro is now also available in R. So it means technically it is not in there. It's not like a package you can just install in R. It's a micro, which is an external, more like an external function someone has created, but you can actually call it into R and use it. Those who use SPSS today, it's a very nice micro for that, but I will entreat you to use R for the analysis. Okay, fine. So that's all about the structural equation modeling. Okay.